chains and champagne shit, every damn thing. I want it all. Houses, expenses, my own business, a truck and a couple of bins. I want it all. Brand new socks and drawers, and I'm ballin' every time I stop and talk to y'all. I want it all. I want it all.
So, example. We're going to calculate, and this is the way they'll have it, is vector line integral, something like that. They have it like this, but I'm going to write it like this. Calculate this. And then they're going to give you a vector field. That would be good. So on this one, it'll be z, y squared, and x. And then the c of t, the parameterized curve. Sometimes they'll give it to you if it's actually like a specified parameterization, such as the following: t plus 1, e to the t, and t squared. But sometimes they'll just give you some curve like the unit circle, and they'll tell you you should know how to parameterize that. And we'll go over that in practice problems as well, how to parameterize curves. And then they also give us that the curve goes from t equals 0 to t equals 2. Okay? So this is all the information that we're given, right? And then we have to make sense of it and compute the vector line integral. So this just means vector line integral. Vector line integral. Okay, so starting off, this is just to identify, this is our A and that's our B. Those are the bounds on t. This technically is our x of t. That's our x component of the t. This is our y of t. And this is our z of t. Okay, so this is our goal. So we want A to B, and then our vector field f of c of t dotted with the first derivative of c of t times dt. Okay, so first of all, I want to start with c prime of t. So let's find that. So we're just going to differentiate with respect to t of each of our components separately. So the derivative of the first one is just going to be 1. Derivative of the second is e to the t. And derivative of the third is going to be 2t. All right, I just differentiated once each of those. Okay, close bracket. And then, so that's this part. So we found that already. That was good. And then the second part, let's find this. So we have f of c of t. So in this case, what we're going to do is we take a look at our f, right? And we're just going to plug in whatever we have in the z spot here. So in this case, that'll be t squared wherever you see a z. So that'll be t squared in for the z spot. And then for the y spot, we have e of e to the t. So e to the t, and that's squared. And then lastly, we have x. So that'll just be t plus 1. Okay? So let's set it up. So we have a to b is now from 0 to 2. And then our f of c of t is t squared, e to the 2t, and t plus 1. All right? And this is going to be dotted with the c prime of t. So that'll be 1 e to the t and 2t. And then we have our dt at the end. All right? So now we'll dot this out on the next slide. So what we get is integral from 0 to 2. And then we have the first components multiplied, so t squared times 1, plus the second components multiplied, so that'll be e to the 2t times an e to the t, right? And then we have plus the third components multiplied, which is t plus 1 times a 2t. Okay? And then dt at the end, of course. All right, now let's just keep going. So we have 0 to 2, and then we have a t squared plus e to the 3t plus a 2t squared plus a 2t. All right, we're getting there. So we have 0 to 2. So we have 3 t squareds. So 3t squareds, 1 2t, and 1 e to the 3t dt. And at this point, I'm just going to break it down into two separate ones. So we have 0 to 2 of 3t squared plus 2t dt. And then the last one here is just I'm going to isolate the e term, So we can use u substitution. So using u substitution, we get u equals 3t, and then du equals 3dt, and then we'll get dt by itself, so we can plug it right into here, right? So that's du over 3. Okay, we'll continue solving on the next line. So then we have, I'll actually integrate that. So what we get is t cubed plus t squared, as t goes from 0 up to 2. And then we have plus, and the integral here, I'm going to replace everything with u's. So we have e to the u, and then dt is replaced by du over 3. All right? So then solving through, we have a 2 to the third plus 2 squared minus 0 to the third plus 0 squared. So that'll be 0. And then plus, and here we have a 1 over 3 e to the u when we integrate. And then on the next step, I'll simplify and replace the u with the t terms. So we have an 8 plus a 4, and then minus 0, okay? And then plus 1/3 e to the 3t, as t goes from 0 up to 2. Okay? So at this point now we'll just plug the rest in and solve. So we get, this equals 12, so 12 plus 1/3 times e to the 3 times 2 minus e to the 0. Okay? So this is 12 plus 1 over 3 e to the 6th minus a 1/3. So the final answer is going to be 1 over 3 e to the 6th, and then this is plus 36 over 3 minus 1 over 3, so plus a 35 over 3. Okay, so that's our final answer for our vector line integral. Alright, so now on to a new topic. So now I'm just gonna, these are also in your book in a table, I believe. But these are properties of vector line integrals. So I just want you guys to be familiar with these vector line integrals. They do come in handy sometimes when you're working with them, as far as simplifying problems and things. So vector line integrals, let's say the vector fields are f and g. Okay, so these are vector fields. And so the first property, pretty important, I'll draw a little squiggly line even, is linearity. Linearity. Okay, and what this means are two conditions. So if we have the vector line integral over some curve of f plus g, and then of course the ds over here, then we can basically just break this up into two separate vector line integrals. So then we have something like this, dot ds, sorry, that has a little arrow there, dot ds, plus, and then we have g separately, dotted with the ds. So these are equal, basically. And then the second condition here is that, or the second thing that's true, second property, is that if you have some constant, k, let's say, so constant k, okay, so then we have f dotted with ds, and this is basically, you could take that out in front. And that's kind of like we've done since we've learned integrals in the very beginning. That is a weird k, hold on, I have to fix that. I think I'll just leave it like that. So then we have the k being out in front, and then you just have your normal line integral here, vector line integral. Okay, and then we have two more headings, or like big properties, which is called reversing orientation is the first one. So reverse orientation, and orientation. So because we are dealing with, I couldn't think of it, because we're dealing with vector line integrals, that means that direction does matter. So direction matters. So basically, if you have a curve and you're traversing it in one way versus another, when you have the negative curve, so that means when you're going, the negative means opposite direction. So opposite direction. When you're traversing a curve in the opposite direction than it's supposed to be, or then it is oriented, that's what it's called, then you can basically just pull the negative out in front, and it will be the negative of, it'll be the negative value of whatever you get when you traverse it in the correct direction. So that's basically all this property is saying, is that when you go in the opposite direction, it's just the negative of the other way around. Okay? And the last one is called additivity. Additivity. Okay? And this is basically saying if C is made of the small curves. Remember we started with those when we were doing scalar line integrals, and that was the whole like Riemann sums, tiny curve thing. So if C, the entire curve, is made of a C1 up to a Cn, and these are like the smaller curves that compose C, then basically we could say that the entire vector line integral over the entire curve is equal to the vector line integrals over each individual tiny curve added to each other. Okay, so this is up to Cn. Okay, alright, so that pretty much does it for the properties. And now we'll go over one last topic. Don't worry, it's not too long. So it's actually called the flux. Okay, so this is an important concept. It'll pop up later in the in this course as well. So flux. Well, let me define first of all. So far, I don't know. I put a comma there. So far, comma. We've been dealing with. We've done the following, and that was f dot t ds, or f dot ds, and then with the little arrow there. But anyways, what this was, if you recall, this is the tangential component. So I'll write it here. So this was the tangential component of f, component of our vector field. Okay. So that was actually, so here's, well, I don't even need to draw that, but here's our curve, right? So that was, here's f, and the tangential component was this thing. So that was f like parallel, or f dot t, okay? So that's what we were looking at so far, along our curve C. But now, what flux is, so flux, this deals with the normal component of a vector field, Okay, so in this case, what we're going to have instead is some curve, right? Some curve going along, and let's say our f is like that, right? Now what we're interested in is not this part here. We're interested in this part, the normal component. So here's our tangent line, right? Let's say our tangent line's here. Normal means perpendicular to the tangent line. So this is our f perpendicular, or normal, okay? So now we're interested in anything going straight across, like perpendicularly across the line, the curve here. So you can say like perpendicular to the curve. Okay, so basically how you would calculate this is if you're, once you calculate c prime of t, remember how that goes along the tangent line? So now what we need to do is make something that is orthogonal or perpendicular to it. So let's say your c prime of t was x prime of t and y prime of t. Okay, so what you're going to do to find your normal is normal vector is going to be switch these. So you're going to swap the two places. Okay, so you're going to have y prime of t and x prime of t, and you're going to stick a negative sign on the x. Okay, so basically when you dot these, you get 0. When you take the dot product, you get 0, because that's a, I guess, a characteristic or a quality of two vectors that are perpendicular to each other. When you take the dot product, it equals 0. So anyways, so that's how you take the normal. And then to normalize the normal vector, what you would do, so what we need is unit normal vector. So unit normal vector, you could say n hat or n arrow, whichever. That's going to equal, again, how you normalize things is you take the original vector and you divide by its magnitude. Okay, so that's how you get the unit normal. And I'll conclude on the next slide. What we have is the flux across C, some curve, is equal to, from A to B, so this is your curve again, the bounds on T. This is going to be equal to, so the beginning is going to look the same, okay? So we have our C of T, because that's just the parameterization for the curve. Now we're dotting it, instead of with the unit tangent, we're going to dot it with the unit normal, okay? So, well, not the unit normal, just kidding. It's actually just going to be the normal vector. Anyways, this is just the normal vector. So normal vector. Okay, not the unit one necessarily. Because it cancels out like the way we did before with the tangent one. Anyway, so this is just the normal vector, not the unit normal. Not unit one. Okay, I just showed that on the last slide just for your information, I guess. Anyways, so then you would solve it like like normal from here. No pun intended, like usual. Anyway, so what the flux is conceptually is the rate of flow of something. Rate of flow. Whoa, I can't spell. Rate of flow across the curve at any time. Okay, so let's say you were to have a curve or something. This is your curve, C of T. And then what this flux here is, because it measures everything that is perpendicular to the tangent line at those points, see here? So we're going across this way. So what it would measure is basically like everything that's flowing through at any given time. Okay? So that concludes this video, and I'll talk to you later if you watch future videos.
Rings, gold chains, and champagne, shit, every damn thing, I want it all. Houses, expenses, my own business, a truck, and a couple of bins, I want it all. Brand new socks and drawers, and I'm balling every time.